Ancient Indian and Greek philosophers have always wondered about the unknown and unseen form of matter. The idea of divisibility of matter was considered long ago, as we have discussed in our very first lecture. Around 400 BC, the Greek philosopher Democritus introduced the idea of atom. His idea was based on philosophical consideration, yet not much experimental work has been done to validate these ideas till 18th century. By the end of 18th century, scientists recognized the difference between elements and compounds and naturally become interested in finding out how and why elements combine and what happens when they combine. Today, we are going to talk about their discoveries and work about atoms. Let's begin the show. After performing much experimentations, Antony L. Lavoisier and Joseph L. Proust laid the foundation of chemical science by establishing two important laws of chemical combination. First one is law of conservation of mass. This concept was discussed and given before Lavoisier in 1748 and 1756. More refined series of experiments were carried out by Lavoisier, who expressed his conclusion in 1773 and popularized the principle of conservation of mass. According to him, this law states that mass can neither be created nor destroyed in a chemical reaction. That is, whatever the chemical reaction has been carried out, net mass before and after reaction will remain same when mass of all products are compared with the mass of all reactants. Second law is the law of constant proportion. This law was given by Proust in 1779. This observation was first made by the English theologian and chemist Joseph Priestley and Lavoisier. According to Proust, this law states that in a chemical substance, the elements are always present in definite proportion by mass. That is, if there is 1 gram of element A and 2 gram of element B in a chemical substance, then their proportionality is 1 is to 2, which will remain same in every case and condition. For example, water. In H2O, the ratio of mass of hydrogen to the mass of oxygen is always 1 is to 8, whatever the source of water is. Thus, if 9 gram of water is decomposed, 1 gram of hydrogen and 8 gram of oxygen are always obtained. In order to give these laws an appropriate explanation, John Dalton proposed a theory named atomic theory. According to this theory, all matter, whether an element, a compound, or a mixture, is composed of small particles called atoms. The postulates of this theory are all matters are made up of very tiny particles called atoms. Atoms are indivisible particles which cannot be created or destroyed in a chemical reaction. Atoms of a given element are identical in mass and chemical properties. Atoms of different elements have different mass and chemical properties. Atoms combine in the ratio of a small whole number to form compounds. The relative number and kinds of atoms are constant in a given compound. After all of these laws and postulates, still the question remains, what is an atom? In a simple language, we can say that the smallest building block of all the matters are known as atom. We can visualize matter as the wall of house and atoms as the brick of wall. These atoms are very small. They are smaller than anything that we can imagine or compare with. More than millions of atoms when stacked would make a layer barely as thick as a sheet of paper. According to experiments, radius of atoms are about 10 raised to the power of negative 10 meter. The most remarkable concept that Dalton's atomic theory proposed was that of the atomic mass. According to him, each element had a characteristic atomic mass. The theory could explain the law of constant proportion so well that scientists were prompted to measure the atomic mass of an atom. Since determining the mass of an individual atom was a relatively difficult task, relative atomic mass were determined using the law of chemical combination and the compounds formed. Relative atomic mass is a concept that allows us to compare the mass of one atom to another. In this concept, we fix an atom as a reference mass and compare others with this atom. In 1961, for a universally accepted atomic mass unit, carbon-12 isotope was chosen as the standard reference for measuring the atomic mass. One atomic mass unit is a mass unit equal to exactly 1/12 the mass of one atom of carbon-12. The relative atomic mass of all elements have been found with respect to an atom of carbon-12. For easiness, imagine a fruit seller selling fruits without any standard weight with him. He takes a watermelon and says this has a mass equal to 12 units. He makes 12 equal pieces of watermelon and finds the mass of each fruit he is selling relative to the mass of one piece of watermelon. Now he sells his fruit by relative fruit mass unit. Similarly, the relative atomic mass of the atom of an element is defined as the average mass of the atom and compared to 1/12 the mass of one carbon atom. Dalton was the first scientist to use the symbol of element in a very specific sense. When he used a symbol for an element, he also meant a definite quantity of that element, that is, one atom of that element. In the beginning, the names of elements were derived from the name of the place where they were found for the first time. For example, the name of copper was taken from Cyprus. Some names were taken from specific colors. For example, gold was taken from the English word meaning yellow. Berzelius suggested that the symbols of elements should be made of one or two letters of the name of elements. Hence, many of the symbols are the first or one or two letters of element's name. The first letter of element is always written in a capital letter and the second letter as a smaller letter. Here are some examples of symbols of some elements that are found from their names. Examples of name in English appearing the letter in the symbols are chlorine, Cl, zinc, Zn. Examples of name in Latin, Greek, and German appearing later in the name are iron, Fe from its Latin name ferrium, sodium, Na from nitrium, potassium K from kalium. That's how each element has a name and a unique chemical symbol. Nowadays, International Union of Pure and Applied Chemistry approves names of elements, that is also known as IUPAC. That's enough for today. For more information about this or any episode of the series, check out the blog. Link is in the description. We have additional contents, further readings, and transcripts of every show. If you value the show and educational resources and wanna help keep it going, subscribe the channel and also subscribe our blog. Or alternatively, you can like, comment and share the show. It may be just a click for you, but every little bit adds up. Thanks for coming to the channel and watching the video. I hope you loved the show.